There's an announcement. So the offline participants have not yet arrived after having dinner. So we'll postpone our lecture by 15 minutes. So we'll start at 2:30. Yeah, so we'll be following this schedule throughout 5 days. Did I say dinner? Oh, sorry.
It happens.
Hey. डुअल करोगे है ना फंक्टर्स का डेफिनेशन उसके बाद एक I'll try forgetful maybe vector maybe I don't know which one I'll do maybe ये भी कर सकता हूँ पोसेट जो भी है टोपोलॉजी और पोसेट भी कर सकता हूँ टॉप टू सेट्स forgetful no this one जो connecting वाला है either of them
पूछना और स्टार्ट करना पूछना एक बार सब लोग इंटरेस्टेड करके फिर करनी स्टार्ट कोई नहीं गया है छोड़ के स्टार्ट कर हम 1.5 घंटा लेंगे 5 मिनट एक्स्ट्रा लेंगे
So let's our second.
Are people ready? लोग ready है कि नहीं? Start करो। सामने कैमरा में
okay
So can we start now? Hello. Now I asked to the online students participant. Can we start now? Hello. There is everyone. Is there anyone in online? Yeah. Yes. So. Okay. So.
sure
लोग हाँ बोल रहे हैं 5 लोगों ने हाँ बोल दिया
Okay, now we start our second session for this day. So, oh, sorry, third. Yeah. So this is the first session after lunch. So for this session, we have two speakers. One is Dipankar Maity, and second one is Animesh Renanse. Yeah. So Dipankar just complete her BSMS from ISER Pune. He's in research interest in category theory, higher category theory, and homotopy theory and topos. And he is the first for first lecture for this session, speaker for these sessions, and then Animesh. So Animesh is a background is electrical engineering. He just completed his graduate from IIT Guwahati. So previously he worked with Professor Amit Kuber Topos theory, and now he's currently doing his bachelor thesis with his professor Rupam Bhatt on generalized Galois connections. Okay, so now up to you.
Okay, thanks for the introduction. So I hope this extended time have given you an opportunity to finish your lunch. But for the rest 1.5 hours, this might still be heavy for you. So we'll try to digest mathematics instead of your food. So, yeah. Okay. So let me ask this question to you. What is mathematics? Or rather, what do you do in mathematics? Well, I'm going to talk about category theory.
Please write down.
Okay.
Leave this space, just even below.
Yeah. So I'm going to talk about category theory, which is going to be some sort of an enzyme to digest mathematics in some sense. So for the last 2 lectures, you have seen 2 different notions in mathematics. One was posets and another was topologies. You might think that, oh, mathematics is so diverse. They are 2 different languages. But I believe that in the end, when she was talking about specialization, you have seen that how you can go from topology to poset. Given a topology, you can form a poset out of it, right? Some sort of connection. And she told you about some theorems that you can prove when a topological space is T0, T1 using the poset property that she introduced. So in some sense, you might have different theories in mathematics, but they do talk to each other. What category theory does is gives you a tool to talk about all of this all together so that you can translate notions from one to the other. In other sense, if you really want to understand what category theory is, you might search in the internet. Then one of the famous answers you get is that it gives you a bird's eye view of mathematics. Let's elaborate this point. Instead of a bird, you think of yourself, you are going to a new society. So this is a mathematical society, let's say. So it's a mathematical theory for us. So if you're going to that society, you'll find people inside. A society is but its people. And then between people, you will realize that peoples are having opinions about others. So if A is a person, he might have some opinion about another person B. Okay. And then if you ask A, then A will tell you something about B. Of course, he can have many opinions about a person. But note that if in a society, if you have 3 persons and let's say A, B, C, A is having some opinion about B and B is having some opinion about C. Once B tells you, if you are A, once B tells you what is his opinion about C, you are straight away going to make some opinion about C, right? So this is some sort of law of going from A to C via B. In a mathematical theory, you realize that the theories are some sort of structure like this. So in the first lecture, you have seen that there are posets, and so these are all posets, let's say, in the first lecture. And then these opinions are those order preserving morphisms which they talked about. And what do? They tell you something. It is some sort of assignment which transfer information from one to the other, right? So I'm going to define a category in this way. Yeah, sure. So the categories is going to model a mathematical theory in some sense. And what it is supposed to have is, as you noted, it is supposed to have a collection of persons inside, which I'm going to call as objects. So a category C, I'll define now formally. A category C
category C has this structure as a society. It has a collection of objects who live inside, and between any two objects, so given any two objects, A, B inside C, you have a set of maps between them, some sort of opinions. So you have, there exists, or you are given a set of morphism denoted home AB. So a set, all right, sets. So a set for every pair of object. And note that just like you could make an opinion of C via B, you have the notion of composition over here, which is if you have a morphism from A to B. So these things are I'm going to call as morphism. Whatever lie inside is a morphism. Okay. And the law of composition is given by this. If you have two morphisms which are connected via B, then you can straight away assign a morphism from A to C, written G after F. What else do you have? Okay, in a society, you have some sort of null opinion about yourself. You are not really careful about your no opinion about yourself. That is a null relation, which is not really going to change your opinion. So let's say you have an opinion about B, and B is having a null opinion about him. It is not really going to change the opinion. So in some sense, you have for every person A in C, some sort of particular morphism in the home, which sort of does nothing when composition is considered. Meaning that if you have a morphism from A to B, then F compose 1A is F. Or if you have a morphism from, let's say, D to A, G, then 1A compose G is going to be G again. G might be a bad notation, but let's take that. So that is one. And of course, whenever you do some theory in mathematics, you have seen this notion of associativity, which somehow tells you how you can avoid ambiguities. So you can have, let's say, a chain like this of morphism, A to B to C to D, say H, G, and F. Then if I ask you to compose these three, some of you might say, oh, I have composed this two first, then I'm composing this. Or someone from here can say that I have composed F and G first, then I'm composing H. That should be some sort of some ambiguity sounding. So to make it unambiguous, what you do is you declare this property that for all H, G, F, whenever you can compose, this has to hold. So all I'm trying to do is trying to make it simple so that things become easy for us. So a category is a mathematical structure which has this as its structures and this too as properties. Star, this star. So the structure consists of object, morphism, law of composition, and identity. And the properties are these things, which is the one property for identity and another property for composition law. Okay, so that is what a model for a mathematical theory should look like, which I'm going to call category. All right. So what should be examples now? Like I said, mathematical theories are being modeled by category theory. Tell me about mathematical theories that you can think of. So here, let's say, so the first talk was on posets, as I said. So if you take posets, I'm trying to construct this category denoted posets tilde, where as objects, I'm going to take all posets. Oh, yeah, okay. So as objects, I'm going to take all posets. And how do they talk to each other? Well, morphisms. Okay. Okay, bear me, just bear with me for this time. So as morphism, you take order preserving morphism. So, and convince yourself that you do have identity there and law of composition there, and these two properties hold. Okay, so convince yourself. Now, what about others? What about the second lecture? You have topology. I'm going to denote this by top. What are the objects in this theory? Well, the objects are all topological spaces. And what are the morphism? Well, the interesting morphism that Purvita talked about are continuous map, right? So that is one category. So you can actually make it a table, right? So these were first two lectures. Now tell me about your favorite mathematical theory. Of course. Yeah, of course. This is not the only theory that you can study in sets. In let's say top, you can take maps up to homotopy. You can do so many things there. Just have to make sure that this properties hold and this structure is available. Okay. You can have many. I'll give you some example in the latter course that you can actually have many categorical structure with the same objects. Okay. I'll come back to that. So, yeah. Now, someone, does any one of you want to tell me what your favorite theory is? Groups, right?
We can take
Then-
like all groups and
Right, all groups. And
mapping can be like any multiplication, any kind of within that elements, or some kind of group homeomorphism.
yeah, group homomorphism, the correct word. Group homomorphism. So this is going to give you the category of groups, noted GIP. Anyone else? Your favorite theory in mathematics? Huh? Rings.
Same as rings.
All right. These are all algebraic examples. You have rings. Where would you want to put it here?
All rings.
Sorry,
All
all rings.
rings.
All rings. Okay.
Ring homomorphisms.
Ring homomorphism. Okay. So some people do take only unital rings, but that's okay. Any non-algebraic ones? Metric spaces. Okay. What do you want to put in here? In objects. What do you want me to put in here?
All metric spaces
All
and
metric
then
spaces.
homeomorphisms.
Spaces. And
Uh, homeomorphisms between the metric spaces.
homeomorphisms.
Yeah.
All right, you can do that. Of course, why not? So, just you have to make sure that this law of composition is available. You know that composition of two homeomorphism is again a homeomorphism. Therefore, you can really make it a category. Of course, as you said, can you have more than one category? Yeah, homeomorphism is giving you one. Then in metric spaces, you can have continuous maps once again. And then other than that, you can have metric preserving morphisms. Oh, I see. Okay. So this is continuous maps. You can have metric preserving morphisms, but that's, you can keep on adding. Anything else? Huh? Sets. So that's more fundamental. Sets. What do you want me to put in here? All sets. And as morphisms?
Functions.
Functions. Yeah. Functions. Yeah. So yeah. Yeah. So this is a hybrid mode. I forgot. So do you have any some chats? Does any online participant want me? Yeah. So is there anyone in the online mode who wants me to tell about some of their favorite theories?
Complexity theory.
complexity theory. Okay, so I'm so sorry. I don't know what a complexity theory is. So pardon me. I'm so sorry. Anything else? Okay, that's all for now. If you can think of, then come back later and fill up this diagram. I'll leave that for you. But now, as I said, I'm going to digest mathematics. So so far we have collected all objects and made it a category. What about a single particular object in a category? Let me come to this category. Let's say. What is a group? I'm going to tell you that category theory is so flexible that not all groups, in particular a single group, is going to give you a category. This is so nice. How I am going to do that? Will someone, so you pointed out groups. What is a group?
Group is a structure.
No, what is a group? First of all, it's a set, right?
Yeah, it's
Then
a set.
It's a set. I'll write G here.
It has properties like we can a dot b is equal
So you
to,
have a dot,
yeah,
which is a binary relation,
a dot b equals b dot
a
a.
binary function. Yeah, and then
A dot b equals b dot a.
that's a commutative group.
Closure associative and
Yeah.
commutative.
So I'll tell you what
Identity
other properties
inverse.
you have. You have identity.
Yeah.
Of course, you can have inverses to every element, but for the moment, let's forget about that. And
Operations on elements belongs in the group itself.
yeah, which means this is a binary operation. So this is G cross G to G, a dot, or a circle I'll put, or maybe anything you like, a dot. Yeah. So you have, no, that is not the whole story. You have the law of associativity there, and you have the multiplication via identity returning you the same element. Do you see that they are somehow similar to this property and this property of a category? Does that not tell you that a group should behave like a category? Well, indeed. What you do is you make it a category in this way. So I am going to define the category, let's say G. What you do is you take a single object, and as morphisms from it to itself, you take the elements of the group. So you can have, let's say, two elements, R and S. So this is a morphism from star to star and star to star. So you should be able to compose, or in other words, you have star to star, which is R, and then star to star, you have S. You should be able to compose, right? So I'm going to declare the homes in G as from star to star as G itself. And how you are going to compose, you are going to simply write S compose R as S times R. Now check that this property is being satisfied, and therefore a group becomes a category. What about other categories? Well, why not posets? So we started with poset. The first lecture was on posets. What about posets? Can anyone tell me what a poset is? This is a good time to recall what you heard in the first lecture. What is a poset? So it is a set with a binary relation,
such that the relation is reflexive, transitive, and antisymmetric. So for now, you have also heard of pre-orders. That would also do. But anyway, let's take a poset. This is this property that if x is less than equal to y and y is less than equal to z, then this implies x is less than equal to z. Now look at the structure, this particular structure in a category. Does this structure look similar to you in there? Yeah.
Does this not tell you that you can treat this less than equal to as a morphism? So this is what I'm going to do now. So you declare, find this category P in this way. So it's object. As objects, you take the set P itself, and between two objects, you declare the home as a single element, home x comma y as a single element. I'll just write if it is 1, if x is less than equal to y, or 0 otherwise. Meaning that there is a morphism from x to y, you choose your favorite notation that you want to put for x less than equal to y. But nonetheless, there is a morphism from x to y if and only if x is less than equal to y.
So that is my category structure. Now that this is also there, you see the transitivity law is actually the structure of category as composition. You can really boil that down. Now, what about other properties like identities? Do you think it has identity?
Yeah.
How?
Every element is smaller, greater than, equal to itself.
Yeah, so reflexivity. You have x less than equal to y, x itself. And by this definition, therefore, there should be an arrow from x to x. And that I'm going to declare as 1 of x. Okay, from x to x. Does that really tell you that all these things are being satisfied? Check, yes. So what I have done in this two part of the board is on one side, you have a category with a single object and many morphisms. On the other hand, in a poset, you have many objects, but a single morphism between them. So in some sense, this is some simple categories. One category is the extreme point where you have a single object. So it's smallest one in the breadth of object. This is the smallest one in the breadth of morphisms, right? So these are two extremes. So you can think of a category as being some sort of a generalization of these two structures. Okay. Now, great. It all looks very great.
There is a question.
Yeah, sure.
What are the objects in the category?
There is a single object. You put your favorite object of choice, just any symbol, let's say star would do this. Does that answer your question?
Yes.
So this is the notation for the category. I define this capital P, right? So this is the notation for the category. So define P as follows, as a category whose objects is the set P, and between two. Yeah, this set is given to you. This poset is given to you. Given a poset.
The online person.
Oh, yeah. So I said so define G as
Ask him to talk to you.
yeah. So why don't you speak up? Why don't you speak up, Suyesh?
Suyash, can you say something?
Oh, sir, I've got it. The only element was a single.
You're not
piece.
audible. Sorry, which one? So I just so you put in your favorite notation for this. So this is just to I'm just trying to say that there is a single morphism between x to y if x is less than equal to y. By cardinality, I mean that. So I mean, okay, I'll not erase it. So I'll elaborate it. So there is a single morphism x to y if and only if x is less than equal to y. You can put in any favorite relation that you want. You can say this is the notation for this. So you just put in a morphism, a single morphism if x is less than equal to y. Just a name for that. You just name it. This is no. So P, so the categorical structure here I'll draw. These are points in P. And this less than equal to is the arrow. Just a single. This is the picture. Yeah, so even if you think of the Hasse diagram, then these are the objects in this category. So let's say you have a poset like this. So this dots are the objects and this relations are the arrows. Okay. So can Suyash speak up now?
Suyash, no. So he said he understood.
Okay. So now if that is done, then what I want to do next is that, oh, by the way, we were here in posets. So do you remember the speaker talking about what a dual of a poset is? Do you remember that? How was that defined? Yeah, you reverse the relation. So given P less than equal to, you can form a dual to this, which is P delta, and then this by less than equal to delta, where you said that in this structure, x is less equal to y delta, if and only if y is less equal to x in this poset, right? So that is a dual notion. Now, just a moment ago, I said that a category is a generalization of a poset. You can ask me, can you do this this transition in a category? Given a category, can you somehow reverse the direction of arrows and get a new category out of it? The answer is yes. No, which part to erase? But I'll erase this. Okay, I have a part left. Yes. So how do you do that? So I'm going to define next a dual category. So given a category, C, define C of as the following category. As objects, you do nothing, just fix the objects. Just as you did not change the poset, so the objects of C of is still going to be C for me, objects of C. Okay. And just like you reverse the direction of arrow, you say that in C of, you have an arrow from A to B. If, so this is in C of. In C of, if you have a map from B to A in C, means you have just reversed the direction of arrow. To write down formally, you can say that the home in C of A comma B is just the home in C of B comma A. Is that clear? So that is one part of structure of a category. What other structures do you have? So this is done. What other structure do you have? You have the notion of composition in a category. How do you define composition in here? C of. Okay, let's say you have a chain of maps. Let's say A to B. So I'll write C of here. In C of, you have, let's say, A to B a map, and from B to C, you have a map in C of, which means what? Actually, in C, you have this one, but in the reverse direction. But now we can compose this two arrow and take its opposite, in the sense that you have, therefore, you have a morphism from C to A in C, which means you have a morphism from A to C in C of. So I'll denote this. So given if you have a map from B to A in C, then you denote this by F op, let's say. Then if you have F op here and G of here, then you can think of this as an actual map F and an actual map G, and this is the actual composition F compose G in C. Then you can just call it as, let's say, F compose G op. Right? You just define it that way. So what I have done is that I have defined G op compose F op as F compose G op. Is this visible even? I don't know. But anyway, verbally this should be clear. That is a very small space. Anyway, so that is the structures of a category. What do you have as identity? What do you want me to put as identity there? Take identity itself. So as 1A op. So in C op, you put in this as 1 itself, 1A. A to A, you need a map only, which respects composition. So yeah, given a category, you can form a dual category, just as you could do in case of posets. Right. I could talk more about this and I could go on, but this is a very short amount of time. What I'll do now is I'll ask you, what do you do next in mathematics when you study a theory? So first of all, you study what are the things that you are going to talk about. As in groups, you study groups first, define what a group is. Then you talk about morphism between them. What are they? They're structure preserving functions, structure preserving assignment. You can ask me, oh, you are still doing a theory in mathematics. Can you not do anything in that? I'll say yes. So the natural question to ask is that how can you transfer data or structure from one category to another, just as you do in any other categories? Oh, by the way, before I do all these things, is there any question from the online participant? I see that offline participant does not have question. No, right? Okay. Oh, if there is, okay, there is a question. So will the dual of a monoid will be the same category? Well, the homes are going to be the same thing, but note that the composition law. So first of all, when you say that same category, what do you mean by same? You mean to say that everything is same? Is that what you mean? Then note that in a monoid, you do not have the relation that S times R is equal to R times S. Yeah, the homes are going to be the same, of course. The homes are going to be the same because there is a single object, right? But note that composition is not going to be exactly equal, right? S time R and R time S are not the same thing. Therefore, they're not exactly equal. Yeah. So now let me come back to the idea of transferring data from one category to another. This is what I'm going to call as a functor. The name suggests that it came from functions. So what shall it do? You preserve structures, right? When you talk about group homomorphism, what structures does a group have? You have a set, you set elements to elements, and then you have multiplication operation. You assure that, okay, multiplication operation is being preserved, and an identity for your for the completion. You should be able to do the same here. You should be saying the same here. What structure does a category have? Well, these are the structure listed. So you have objects here. You should be able to assign objects to objects. That is, given any object C in C, you should be able to send it to an object. I'll write it as FC in D. What else do you have in a category as structure? Well, given two objects C and C prime, you have a morphism F. So you are also assigning to C prime, you are assigning F C prime. If you are having a morphism A from C to C prime, that is part of a structure of a category, you should also be able to assign a morphism from FC to FC prime, right? That I'm going to denote as FF. What other structure do you have? Well, you have this thing, which is composition. Just like group homomorphism, I wish to have an assignment which preserves the composition, meaning that in the codomain category D, this is going to happen. FG compose FF. So this composition is happening in D. So it is preserving that structure. What other structure do you have? Identity, right? So I impose the condition that this better preserves identity. Because A is being sent to FA, it should also take identity to identity. So that's what a natural assignment should be in the sense of categories. Okay. Now, once I have defined this, you might ask me, oh, what is an example of a functor? I'll give you one, which is sort of coming back to, I don't know which part to erase, sort of coming back to, I'll erase this part. Coming back to the first and the second lecture, I'll try to connect them. As I started by saying that, oh, you have in the first lecture, you have posets, and in the second lecture, you have topologies. I want to connect them via what C talked about, spatialization, or giving a poset structure to a topological space. So here you take the category of topological space, let's say. And also you have heard of p-orders, right? In the previous lecture, what C told you that given a topological space X tau, you can assign a relation X on this, which is reflexive and transitive. That is the pre-order, right? So therefore, to an object in topological space, you are assigning a pre-order to this. So that is an object-wise assignment. Look at the definition of a functor. I've got an object-wise assignment. Then you should be asking me, oh, if there is a continuous map in the sense as you talked about in this example, if you have, let's say, two topological spaces, tau x and tau y, and a continuous map between them, F, right? And corresponding to that, you have y less than equal. Do you have a map from this to this? Well, F is already a map from X to Y. I'm going to send F to F itself with this. But then you have to check that this is really going to be a map of pre-orders, meaning it is order preserving, which means that you have to check that if X is less than equal to Y, then in X, then Fx is also less than equal to Y, Fy. And this is in Y. That you have to check, right? Now use the properties of defining this relation. This is an exercise for you. I leave it as an exercise that check that this holds. This holds. This is. Then you have that as morphism, and then check that composition goes to composition and identity go to identity. That I'll leave as an exercise for you. So what this is doing now, so this becomes a functor in that sense. What this is doing now, it is really connecting lecture 1 and lecture 2. You can ask question in lecture 2, when is a topological space T0? You come here in a different theory. Let's say you are an order theorist, and let's say he is a topologist. You teach him what is the topological space and ask him what is T0. Where is the topological space T0? Then you say, oh, look at this pre-order. This I know has some property which is anti-symmetric. If that is anti-symmetric, the last theorem in the second lecture will tell you that this is going to be T0, right? So in that way, you two can really talk to each other, even though you are two different mathematicians, right? So this is an unification of mathematics in this sense. I'll stop here. If there are any other questions, you can ask. The next part will be a continuation from here. Animesh will talk about some further example of functors and something called natural transformation, which is really natural to mathematics. You'll have a view of that. Anyway, if there are no questions, is there any question from online participants? If not, this one, okay. I'll erase some part here. So what was the relation that you defined? What did Purbita define it as a relation? What was the definition? Tell me. You tell me, then I'll deduce it for you.
So I don't remember it.
Okay, I'll write that for you. So let's say there is an open set in tau, so which contains X. Let's say open, right? Let's say O is an open set in tau X. And assume that, so X is less than equal to Y if this implies Y belong to O. So for any open set which contains X, also contains Y, then you call it X is less than equal to Y. You define X is less than equal to Y. So for this to be true, therefore, in Y, Fx less than equal to Y, what do you want? You want to take, let's say, an open set, take T as an open set in Y, in tau Y. Then you have to show that, Fy belong to tau Y, right?
Yeah.
But now Fx belong to T, implies that x belong to f inverse of t. But f is a continuous function, right? So f inverse t is open. So this really belongs to tau x, right?
Yeah.
Now x belong to tau x and x is less than equal to y. What does that tell you? It means that y is also in f inverse t. This implies y belong to f inverse of t, which means that f of I belong to t, right? And that there you have it. You started with this and you ended at f I belong to t, where t was arbitrary. Therefore, it is really happening and you are done. Well, I am done. You may still have to sit here and listen to. So, no other questions? Nothing? No online question? Then I leave and Animesh will take care of the rest. Oh, yeah, sorry. I thought it is mine.
Okay.
Hello. Yeah.
So far, what we have seen is a grand, a very abstract mathematical object called a category. Just like any other mathematical object, it also has a notion. Oh yeah, sorry. Oh yeah, that's fine. Yeah, sorry. So just like any mathematical object, it also has an associated notion of morphism between two such objects. That is called a functor, which I unfortunately erased half of it. And so one should think of a functor is to category what a group homomorphism is to a group. They are notions of change between two objects of same species. Let me first remove my correct my mistake. Okay, so let's begin with something very simple. This is a very simple category. You have one object. You begin with a group G. You take any arbitrary abstract symbol, star, and every arrow, the only arrow that can be in this category will be from star to star, and define every arrow to be an element of the group. And the composition acts as the multiplication of the group. Let's see what will be the notion of group homomorphisms in that case. That is, how will group homomorphisms translate to in our new language? So let's take any two groups, G and H. And this is a group homomorphism. What do you have here? What does group homomorphism do? The special thing about group homomorphism is that it preserves the products. So if you have G1 here and you're multiplying G2 here, G1, G2 being elements of G, you apply F to it and you get F G1 times G2, which is supposed to be, which is defined to be equal to F G1 times F G2. So that's in the ordinary language of group theory. Let's see what this will tell us about when we translate G into a group, into a category, and H into a category with single object, what it will look like. So let's see. This is a category. The single object present in this category, let me denote it by an abstract symbol star. This is the category corresponding to this group, and the object of the unique object here I will denote by delta. Let me give you a functor between them. It's a functor. What is it supposed to do? Well, it is supposed to take objects to objects. So it will take object to object there's only one object here, so it should map that to the only object that is present here, delta. Any map between objects, this will be an element of the group G, say G. It is supposed to take G to another arrow in this category. So so that will be say FG. F is supposed to preserve compositions. Compositions are exactly the multiplications of this. So what I can write, if I can write here, that F of, if I have one element G1 here, which I am treating as an arrow, and another element G2, which I'm treating as an arrow, this should be written as F G1 composed with FG2 in the category H. But composition is multiplication, and both in G and both in H. So this is exactly the notion of a group homomorphism. In fact, if I define FG, I define FG to be exactly what the small f, the group homomorphism in the ordinary sense is doing, then I get that F is exactly the representation of group homomorphism F in the language of category theory. So that's one example where we translated the whole group theory into the language of category theory, and in the language of very special categories, that is categories with one object. Okay, that's a very simple example. Let's go a bit bigger. Let us begin with a poset, and not just one poset, because we want to have a map between posets, so two posets. And we learned that every poset is a category. So let me treat this as a category, and let me have this functor between them, any functor. What I want to see is that the functor preserves the structures of a category, and the structure of a category when the category is a poset is very special. So let's see what being a functor here translates to in the language of posets itself. Here, so if you have X, which is above Y, so okay, sorry, let me not confuse anyone. Right. So X will be taken to Fx, Y will be taken to Fy, and we know that F is a functor. It will preserve arrows. So the direction of arrow here is from X to Y. So this and since the arrows in a poset are represented by the order relation that is in it, in particular, you should think of X less than Y as X to Y. So therefore, I will have to do this. In fact, F is a functor, so it has to follow this. And anyone like to tell?
Participants can't see the board.
All right. Let me repeat. So you have a poset, two posets. You have a functor between them. I'm treating them, the posets, as a category. Because functor is supposed to take objects to objects, so X will be taken to Fx, Y will be taken to Fy. A relation is interpreted as an arrow. Functor is supposed to preserve arrow, so I get that whenever X is less than Y, this implies that Fx will be less than Fy. And will anyone like to tell me what this means in terms of maps between posets? You can think of F as a map. Perfect. Yes.
It's to the order preserving map.
Yes. Yes, it is. So functors between posets, correspond to let me write like this: monotone maps between posets. Monotone maps between posets. There's an equivalence because even though I showed you one side, that being a functor is having a functor gives you a monotone map. You can easily check that a monotone map will also give you a functor. So that's one special thing, and we are seeing that how categorical languages giving us EQ, in certain instances is giving us something that we already know very well. So that's the power of the language that we are developing. Okay, so that's a bit more bigger in the sense of the size of the category. We began with single object categories. We are now into, well, probably a lot of objects, but I want to stay a bit more for just 1, 2 or 3 minutes, a bit more abstract. Suppose you have any category. What's the most obvious functor you can think in that case? In your hand is only a single category. Well, would anyone like to? Sorry. Yes, you have one category. Well, what else you can do? Do this assignment, which will take C to C. So every object to itself, and what it should do on maps. Exactly, it will take it to whatever it is. So it's like a 0th example of a functor, but it's in this sense good to have, because you can develop this functor with the only knowledge of having a category. So anyways, that's some. So that's a very simple example. Oh, and just to be clear, you write this as IDC or similarly as 1 sub C, and you can have, yeah, people write usually with these two. Yeah, okay, that is not that much necessary. But let's now come back to some things which we usually study in our courses, things like groups. So suppose I give you, so here we had a category of groups. Not every group might be abelian or may not be commutative. In particular, there are certain groups inside of it which are commutative. Some are not. But I collect those groups which are exactly commutative. This is the category of groups which are abelian and group homomorphisms between them. And in the other side, I'm going to have group. So can someone tell me what exactly is the difference between an abelian group and a group, any ordinary group? So, sorry?
Commutativity.
Exactly, they are commutative. Is that a property or a structure?
Property.
Sorry? Someone from online audience? Right. It's not a structure. The structure on a group is of the binary product that you have. The structure on the group is of the product that you have on the elements, which is a map from G cross G to G. All the 3 axioms of a group that you have, associativity, closure, unitality, and inverses, these are properties. Having another property onto your group, things like being commutative, gives you another group, being a commutative group, abelian group. So if now I'm giving this assignment, this is the category with objects as abelian groups. This is the category with all of the groups. I don't care whether they are abelian or not. So this is an assignment which takes G to G, but it forgets that the groups were abelian. Given any object here, you will not be able to say with any confidence whether that group is abelian or not. So, but given an object here, you will be sure that that group is abelian. So this is that functor which forgets the property of being abelian of a group. And so of course, on objects, it will be the same. A group homomorphism is also irrespective of whether it's abelian or not. In particular, in the definition of a group homomorphism, you never specify that it has to preserve commutativity. It just follows from the other properties. So that transfers very well. So that's one functor. which is called the forgetful function. Sorry, inclusion. Sorry, inclusion. It's the inclusion of abelian groups into groups. In the category of groups, you already have abelian groups sitting inside of it. You just when I denoted this, I just took them out and I'm now including them. In fact, if you like to be much closer to your notations of sets, then you can write that as a functor, inclusion. Okay, that's how you include, that's how you forget properties. Now, this is how you forget structures. So, so suppose you're beginning with something very concrete, real vector spaces. At the very fundamental level, what is a vector space? Anyone? Perfect. It's a set over which we add various axioms that it should be an abelian group. It should have multiplication of scalars coming from reals. And those are different. In fact, they are properties. If I take a vector space V and I map them, and I denote this by mod V, this is the underlying set of V. Remember, here you have sets, here you have vector spaces, and if you take a vector space and you just look at its underlying set, if you just look at its underlying set, that is, you disregard any of the structures that you may have on your vector space. In particular, you should write a vector space like this. It is a set with an addition, with a zero additive inverse, and a lot of other things coming from actions from R. But now I'm not looking at, and now I can faithfully remove this. And now I'm not looking at other things, I'm just looking at the bare set that I have in my hand. This defines a functor. It's not difficult to see. You can take a linear transformation, the arrows here are linear transformations. And it will be mapped to W. A linear transformation is also again at the base, it's a map between sets. So I will just take that as a map between the sets and I'm done. This is a functor. You can check very easily. Identity will be taken to identity. Composition will be preserved. So that's another functor. And note that there's a difference between these two. This forgets the structure. It's an underlying functor. The set which is at the base of all the constructions which I do on that particular set. In particular, I build a vector space from a set and adding a lot of operations and other objects. Oh, okay. So that's forgetting property. That's forgetting structure.
Wouldn't another example be from groups to sets?
Yes, there are many. Actually, most of the examples that one is introduced to in first reading of category theory are underlying functors. You can have underlying functors from almost every category here. Poset to sets will be an underlying functor. You forget the relation that you have on posets. Top to sets will be an underlying functor. You forget the open set topology that you have. You forget the structure of a product in groups. You will get an underlying functor. Similarly for ring, similarly for metric spaces. You forget the metric that you have on your set. So almost all of these categories have an underlying functor to sets. That's correct. Yes. Okay. Look at now. This is an underlying functor. I want to have a similar functor, but in the opposite direction. That is, I can get a set out of a vector space. Can I get a vector space out of a set? Okay, so to get a vector space out of sets, I need to have sets first. That's sets. And I want to map to vector space, real vector space for simplicity. can someone suggest me what is, in your opinion, the obvious way of getting a vector space, real vector space out of a set, say set S? Anyone? Something that, in fact, you get very nice vector spaces, which we all know very well. In fact, sorry, trivial vector space. Maybe you mean to say free vector space? Oh, okay. A vector space with only one element. Okay, yeah, but is that interesting? Because whenever you will have any two sets, if you're mapping everything to this vector space, well, any interesting set map will also be mapped to this unique map, which maps 0 to 0. So that's not much interesting. So yeah, this will be a linear transformation, the trivial map. So, sorry, I don't get it.
Can we prove it for any general linear transformation of
Linear transformation. This is a set. This is not a linear transformation. This is just a set function. I'm here.
We are choosing the vector. We are choosing the another. We are choosing like another vector.
Oh, yeah, we are trying to construct a vector space out of just the information of having a set. I just have a set, and I somehow want to have a real vector space out of it. Yes, we do the following construction. This is called a free vector space construction. I will. So how do you construct this? For every element of set S, you attach a copy of real numbers, the field of real numbers. Just for those who know, to get the point across very clearly, you write this as free real vector space over S. This is you join as many copies of field R as there are elements of S. Okay. Let me first write this completely, then I will explain. So, as many elements in T, map this copy. So, no, S is not. Yeah, these are. Because this is direct sum, so these are finite linear combinations. Okay. Here, I will explain this here. When I write this, I mean that elements here are those. An element here will be a sequence indexed by elements of S, and of what? Of real numbers. So RS is in S, where RS is in R is in R. Okay. For all SNS. So that's an element here, in which there's some. Okay, so this is a very technical condition that in which almost all of them are zeros. The free vector space is given by, maybe I should just say this, free vector space is given, is generated by those vectors which have the standard basis of these are the following vectors, which will be 0. This is the, okay, let me remove this and just write the basis vectors of this vector space, which will be BS. BS will be 0 all the way through, and it will be 1 on the est position. Est position. S is in S. Is that clear? Takes capital S to be, say, 1 singleton. Then you get a real line back. take S to be a set with 2 elements. You get R2, the usual one. And this basis will be then E1 and E2. The standard basis 0, 1, and 1, 0. That is what exactly I'm generalizing.
There is one more answer from the audience that Suyash Srivastava says that any set goes to the vector space of functions from S to real numbers.
Vector space of functions
from S to real number.
And this is a
home S.
Okay.
SR.
Right.
Yeah, that is also a functor.
Okay.
You asked for a functor from sets to vector spaces. He has given another example.
Okay, vectors. Okay.
Home in sets from S to R, S to real numbers.
Right. Okay. Let me see. That's true. Vector, where you take set S and you map to all the set functions that I have from S to R, and you're claiming that this is a functor. Who asked this question? Sorry.
Suyash Srivastava.
Okay. Would Suyash like to tell me what is exactly the structure of real vector space here? How will I multiply a real number with this?
Suyash, you can talk. Yeah.
Addition and multiplication will be component wise, like a scalar can be multiplied to all the.
Okay, so yes, G will be another function, and this will be defined point wise. That's what you're saying, right?
Yeah.
Okay. Fine. Yeah, that's this one. Yeah. Yes. Yeah.
Will that be a functor?
Okay. So yeah, the obvious question is, will that be a functor? Let's see. If you have a set map from S to T F, you will have you will have here home sets T to R. What should I do here? I want to construct a map between vector spaces with this set map. Well, let's analyze what an element here look like. It looks like a function S to R, linear function. Sorry, as a set map. So this will be phi. Say you have a map from S to T. And will I be ever be able to construct a map from S to R to T to R? I have a map F here. I want to fill this gap. Will I be able to fill this gap? In fact, this gives us a very good example of a functor which I was about to explain. You cannot fill this gap by, so by filling this gap, I mean that you have an element phi here and you have a set map here. I want to have a map from T to R. Is this possible to get a map from T to R with this just this information? Possibly not. Sorry, F. Sorry. F of S
to R. Take all maps from F of S to R and 0 output. Left click I write it as.
Okay. Okay. This map that you're telling me, T to R, it will take an element T and will map to?
No, not, yeah. I'm taking T can be written as F of S union T minus F of S.
Yes, yes, okay. Can be.
So, yeah, T can be written as union, they are disjoint.
Yes.
Okay. On T minus S, you put equal to 0, the map.
Okay.
And on that, you take the basis. Are all maps from F of S to R. That is a functor.
Okay.
No, here that is not Hamel basis, this is Hamel basis. I mean, there is a difference between these two things.
Okay.
But both these bases are the same thing. That is without finite combination. This is a finite combination.
Right. Oh, okay. Okay. Right. Yeah. Okay, let me not get into much details.
What you're talking about is hypothesis.
Yes. Right. So here's a construction which takes a set to a vector space, and here's another functor. Sorry, I removed this one, and this is another functor. Okay, let me not touch that. Yeah. So I want you to focus mostly on this functor because it will appear tomorrow also. Right. So that's one example of a functor. The other example, okay, now we are going to some simpler examples, something that we all know, sets, two sets. Such a functor, when defined, will be called an endofunctor. It takes its domain category and codomain categories are same. So the functor which I want to talk about has the following assignment. It takes a set X and maps it to its power set. Okay. And Y will be taken to, again, power set of Y. But if you have a map F from a set map from X to Y, can you define, can you give me a set map from power set of X to power set of Y? Here's a function which will do the job. It will take any element. Here will be a subset of X, and it will just take its image under F. So take any say U that will be in here, and it will map to F. Okay, so yeah, so that defines a functor. We call this the power set functor. Okay, so this is a very simple example of functor. Now, so far what we have been looking at are some examples of functors which well are pretty natural in this sense that things like vector spaces, sets are something that we know about, and these were the first examples of categories. Let me give you in some sense, a synthetic version of a functor, or an artificial one, which we constructed out of just our own immediate need. For that, I need to define the following category. These are finite dimensional vector spaces with a specified choice of basis. That is, an object here will look like a vector space, a finite dimensional vector space, finite dimensional real vector space with a specified choice of a basis here. Say this is n dimensional, so this is a basis. And so let me, and there's another category which is equally different, which are an object in this category is a natural number n. What about maps in this category, finite dimensional vector spaces with specified choice of basis? So if I take another such object in this category, which is from J from 1 to M, of course the map between them, I will take them to be linear transformations. Linear transformation between finite dimensional real vector spaces. I hope you see what this is going to. And I define the arrow between two natural numbers here as a m cross n matrix. All m cross n matrices between will act as a arrow between natural number n to m. So this will be a matrix m cross n. You can check that this forms a category, and so does this. Now, what I'm going to define this functor as of course, I will take this finite dimensional real vector space and I will map to its dimension. So I will write here dimension of V, which will be a finite natural. And similarly, I will on the objects, map dimension of W as M. But what should I do on the level of arrows? I will take a linear transformation between finite dimensional real vector spaces, and we know that this linear transformation has a matrix representation, which we, and this is the reason why we chose a specified choice of basis, because we will get a unique matrix representation here by looking at what are the coordinates of each vector here. Each basis vector here will be in terms of this basis vectors. So let me write that as A sub t, and this will be an M cross N matrix. And this is well defined. And in fact, this is a functor, you can check. And there's not much to check here anyways. So that's one special functor. You will see this functor soon. Most of the functors you will see soon in various different disguises. Okay, so now I want to give you, so that all these examples were very concrete. We were working with vector spaces, real vector spaces, matrices, sets, groups. Now I want to go back again to an abstract level, and I want to again ask what all functors I can get when I have any category C, but not just any category C, with a specified object in it. In particular, I have the category C. Suppose I have a category C and a specified object inside of it. I want to devise functors out of this. Just this scenario. So, well, what you can do first of all, because the definition of a category gives you objects and arrows, so you can maybe try drawing certain diagrams. Well, you can begin with C and take any arrow, D to E, suppose, F. Now, if you have an arrow like this, suppose you have an arrow like this, then you can fill this up, right? Or maybe I will draw all the possibilities. If you have an arrow like this, that's one possibility. Then again, you have F, you have an arrow like this, that's one possibility. This F is fixed. What is fixed for me is C and this arrow. Everything other I can take as my will says. So another possibility can be D to E F. I have an arrow like this, and another possibility is that I have this fixed one, and I have an arrow like this. With this information, I want to fill the remaining gap. You can easily see that I can fill this gap by composing with this. So if my choice was G, then I can fill this by F or G. But here's a problem. How can I fill this without any other information? This doesn't seem to have any natural extension. Remember, we are in arbitrary category, so we cannot right now talk about taking inverses and mapping in that way, or taking complements. And similarly is the case here. I don't know how will I fill this gap, so that clearly doesn't work. But this is interesting. If I have G here, then I can fill this up, and I will get a map from from D to C by composing G and F. In fact, this assignment, having this fixed and this as varying, and this assignment, and similarly this assignment, gives me two functors in this scenario. And now let me write this very concretely. So here are two functors. I will begin with arbitrary category C, and I will map to sets, and I will take C, and this is the fixed object that I began with, and I will map this to, you have a fixed object C in C. So this is given you from the start. So if I take any object, say D here, I will get Hom CD. C was fixed, so this will keep varying. I will have Hom CE, a map here, an arrow here will be taken to this arrow, and this is the case which corresponds to this assignment. I take any arrow here from an arrow G here, and I will map it by composing with F, decomposing with F. And I will get a valid choice, a valid functor. This is called a Hom functor. This is very important. A covariant Hom functor. Because why it's called covariant will be clear by looking at what the other functor which I have. The other functor, since I have no use for this now, so I will remove this. The other functor is the following. Now remember what the dual of a category was. And if you take, and again, C is fixed with you, and you take any object here, I will map it to something different. I will map it to not Hom C to D, but Hom D to C. Yes. What exactly I'm doing here is akin to this. And we'll soon see. And this is an arrow. Don't get confused. This is not an arrow in C of, this is an arrow in C. And what this will be, the action on objects will of course be the same, E to C, but I added an opposite just to counterbalance this phenomena, that I have an arrow from E to C, not from D to C, that I get that I map from D to C. So here this map is going in the opposite direction. I get a map G here, and I at the end get a map from GOF. Okay, so these are, and this is called the contravariant Hom functor because it reverses the directions of the arrows. Okay, so
Animesh,
yes,
you have 10 minutes left.
Sorry,
10 minutes. 10.
Yeah. Okay. Yeah. So that's the last of my example. Yes. Yeah.
There is a question.
Okay. Is this dual of the functor in the previous example? Dual of a functor. You can say that, but that's not precisely defined. You can say that this is the dual functor in the sense that it instead of keeping that direction as it is in the category, it reverses that. So yeah, you can say that if you wish. So that's the yeah. So that these are two important functors which we will see very often. In fact, we will see these two till the last day of this. Okay. Now I want to give you some very special functors. Special functors because you know them very well from your high school days. And these are just generalized to the case when you learn algebra in university. These are notions of determinants of matrices. They also give you functors, but not just functors, something much special. So if you remember, if you have a matrix in, say this is a n cross n matrix over real number, then you can talk about its determinant. It may be 0, it may not be 0. But if it is, we know this also, the characterization of invertible matrices. A matrix is invertible if and only if its determinant is non-zero. That's something that we learned in very long ago. In college, we also learned that you cannot, so you have an n cross n real matrices, but you can also have n cross n matrices over any ring R. Not you can have them, but what I want to focus on, a commutative unital ring, something which is fairly concrete, where R is in a commutative unital ring with unity preserving maps. You can have matrices there also, and you can also have the notion of determinant there. And just like determinant of a real n cross n matrix is non-zero, and non-zero real numbers are exactly invertible real numbers. Similarly, the determinant of such a matrix with entries in any ring R, if it is invertible, will lie in units, the group of units of ring R. That is all those elements of the ring which are invertible. So determinant of M will lie in the group of units. Okay, but that's basic assignments. Let me now rigidly write them. So will anyone like to tell me what is what we call the group of invertible n cross n matrices? Sorry. Yes, we call them general linear group over ring R, or general linear group over reals. So we call them GLN of say R reals. It's the group of n cross n real invertible matrices. Well, I remove this and I put a blank there. And instead of taking R, the real numbers, I will take any commutative unital rings. And I will map to, and I will do, yeah, group. Because taking a ring here, GLN of that ring will be a group. So this goes to R, GLNR. And this is an assignment which also extends to maps. You have a ring, another ring S, you can get GLNS. And if you have a ring map here, say phi, you can have a map between a group homomorphism between them, and that group homomorphism acts pointwise on each matrix. So if you have a matrix here, you define phi of M here, which will take this will have n square entries. Every entry will be mapped by phi. Yeah, that's an you can check that this works. Yes. Yeah, this is a unit preserving. Yes, unital maps from unital ring commit. This is a map of commutative unital rings. Yes. So it's a good exercise to check this works, and it will lead you to definition of determinant as polynomials, phi factoring through all of them, phi preserving identity, and that will work out. What you have to check here is that if this determinant is 0, then its determinant will be 0. Sorry, if this determinant is non-zero, then this determinant will be non-zero. And that's actually fairly easy to see because M will be in the group of units, as we will now say. So another assignment that I want to have is the following: units. If you have a commutative unital ring and it maps to group like this. So if you have a real ring of real numbers, its group of units is R minus 0. You remove 0 and everything else has an inverse, multiplicative inverse. Similarly, you can do for any ring. You can map it to its group of units. You can have S here, say this is the ring map phi. S, you have this group, and phi, since it preserves the multiplicative structure, so unit will be mapped to unit. So this is very trivial to see. So this is again an assignment, and you have two functors. Not just two functors, and these are not just examples of functors, these are more than that. Because if I have GLN R for concreteness, then I get the following map to units of R, which is just R minus 0, which is the determinant function. Every real n cross n matrix will be mapped to this group under the mapping by determinant. And also that this is a group homomorphism because determinant distributes over the product of matrices. But that's not only true for reals, it's true for any ring. And now I need to do this. So this is just the right. And similarly here, and this is true for all. And not only this, because they are functors, so I will have a map from GLN to S, which will be, let me write this as GLN of phi. This map R to S was phi. So we just write GLN of phi. And similarly, you have this map, units of S. This is just literally just phi, because units are taken to units in ring maps. And again, we have landed the same story we can repeat here, and we have a map which will take determinant of n cross n matrices, invertible matrices with entries in S, and it will map the determinant, which will be an element of a group of units. And if you track this around, take any matrix here, you get its matrix, its determinant, it will be an element here. And by mapping by phi, you will get this phi of determinant of M, which will land in the units of S. And similarly, if you take this one, this will be phi of M, and by like this, and you will map via determinant. It will be determinant of this matrix, and one because phi is a ring homomorphism between commutative unital rings, you can check yourself that this is same as this. In particular, this diagram commutes, and this is a phenomena that happens a lot of times in mathematics. In fact, so much so that we need to have a concrete definition. Yes, let me just write in 2 minutes a definition, which we will elaborate later on. So this is a phenomena which happens a lot of times in mathematics. You have two functors like this on the same domain and codomain categories, and at the end you get very obvious looking maps between them, which when you and one for each element of the domain category, you get a map in the codomain category, and the obvious square that you can make commutes. These are exactly this thing, determinant is a natural transformation. Natural. Right, sorry. The determinant is a natural transformation. What this precisely means, I will talk tomorrow. So yeah, that's the main crux. Something which we know from very early on in our lives turns out to be natural in very precise sense. So yeah, that's all I have.
Any questions?
Just a clarification. Someone asked earlier that can you have different structures on the same object? I gave you some, which are homeomorphism, continuous, and mate. Just a moment ago, he wrote an example which is matter. There you see you have natural number, but morphisms are not anywhere functions. They are matrices. You can have poset structure there. That's a different category, but he just gave you another one. You can construct more maybe.
Any more questions from the online audience? Well, thank you. Online people don't have any question. So Yeah. Thank you very much.
So we have no. Okay, now there is 15 minutes tea sessions. Then okay, so then we start our tutorial. Okay, 4. Yeah, 4:15. Okay.
Rita, can you hear me? Purvita, can you hear me?
Can you hear me now?
Yeah, I can.
Yeah. Actually, the mic was not working.
So I'm wondering, I don't know how many of them will stay back for the tutorials, but
That also I don't know, but
yeah, but in any case, we might have 2 rooms, isn't it?
I guess that if it is, I can see 33 participants right now. Maybe we can break it down like one online session and another is about just the offline people. How about it? Because I don't know how
I'm
many
saying
of them
online is 33. That's why I'm commenting.
Oh, you want to break out the online mode into session? I mean, 2 groups, right?
Yeah, that's what I was suggesting, but it's up to you all.
Yeah, I have no problem because we do have enough tutors.
So since we do have the tutors, that's why I'm suggesting.
So yeah, it's better actually because here in the offline mode, we have around 13 people. And if we break down the room for online meeting, then it is becoming the same number.
Yeah, same number. That's why I suggested.
Okay, yeah, that can be done. Yeah. Okay, so I'm just going to, I'm trying to make break the room, having in one room Chandrima and another room with Obhijit.
Yeah, sure.
And I'm keeping Bidhan and Prashanjit for the offline people. And we will be there around.
Yeah, sure.
Will it be fine? I think it's good. It's good enough to do. Because like from here, if I just assign someone to the online mode, then it will be disturbed, I guess, for the offline people. So better to give the, let us see like how it will go. If there is some need, I can just assign Bidhan to the online mode again with someone.
Sure, we can do that.
Okay, I'm just trying to break out the room now. অন্যয় বলছি রুমটা ব্রেক করার একটা ব্যবস্থা কর মানে অনলাইনটা হ্যাঁ দুটো করতে হবে দুটোর মধ্যে একটাতে क्या ओ ऑप्शन एक तो अम्पन्ना है दोनों ही सेम है हाँ हाँ और you brought something I don't know what it is
Even I don't know. I have to open and see.
yeah so একটু রুমটা ব্রেক আউট করে দে হ্যাঁ এখনই করে দে এখন করে দিলে অবশ্য আমরা যেটা অ্যানাউন্স করব সেটা সবাই শুনতে পাবে I mean whatever we will announce breakout করতে কতক্ষণ লাগে just a second kind of okay so maybe after some time we can আগে আমি বলে নি তারপরে তুই ব্রেক করে দিবি তার মধ্যে একটা রুমে হচ্ছে চন্দ্রিমাকে রাখবি আর একটা রুমে হচ্ছে অভিজিৎকে রাখবি মানে ওটা নিশ্চয়ই অ্যাসাইন করা যাবে ফ্রম হিয়ার তো একটা রুমের টিউটর ওরা থাকবে সেটা আর আরেকটা রুমের টিউটর হচ্ছে চন্দ্রিমা থাকবে আর বাকিটা হচ্ছে এখান থেকে করবে আর যদি দরকার লাগে তখন ইয়েকেও দিয়ে দেবো কি নাম বিধানকে হচ্ছে অনলাইনে কোথাও একটা ঢুকিয়ে দেবো মানে অভিজিতের সাথে ঠিক আছে পারবি তো করতে এটা লাস্ট মোমেন্টে ওকে ফাইন Oh, email about what? I forget.
फॉरगेट क्या प्रेस रिलीज के लिए क्या देना है?
चलो चलो लिखते देते हैं। Okay, so everyone can listen to me. I mean, I'm talking with the online participants. Yeah, there are some chats, I think. Let me see what is there. That is not needed, right? Okay. So all of you can listen, can hear me? Am I audible?
Yes.
Can anyone? I can't hear anyone of.
Yes, you are audible.
Oh, but I can't hear you properly. Can
Yeah,
yeah, now I can. Now I can hear Sujata properly. Yeah, that's good. Okay, so we are going to start with the tutorial session. So Sujata, do we want to ask them to spend that first half on your tutorials, I mean the exercises, and then the second half on the topology exercises. Will it be good, or they can choose any one of? Okay, so
they can just, so there are both exercise sheets, I think, are available, isn't it?
Yes, yes. So for the online participants, I want to mention that please go to that course materials and you will find the exercises there over the website. And Amit, could you please attach it in the chat box so that they can easily get it? So anyways, at the chat box also we are going, you are going to get the exercises on order theory. And I already provided you with my lecture notes, and there I already noted some of the exercises and I leave some of the proof of the theorems. So during the tutorial session, you're supposed to solve this, and if you are stuck with some problems, you are going to ask your tutors first. Okay, so here is the plan. We are going to, like, as I can see 31 participants, we are going to break the room in 2 rooms. So 15 each will contain, and one of the room will be with the tutor Abhijit Ghosh, and the second room will be with the tutor Chandrima Koyal. And for the offline participants, we do have Bidhan and Prosenjit. So they will take care about it wherever you will stop. And I will insist you to spend your first half on at looking at the order theoretic exercise and then topology, and you can mix it, no problem, but try to do it, and whenever you stuck with something, please ask your tutor. Okay, so Amit, please break out the room. So you all of you already get the questions, right? The exercises by Sujata Di on the order. Okay, very good, very good. Yeah. So, if the room is already broken or not really yet? Okay, so you could see that Amit Kuber is inviting you to join either room 1 or room 2. Please like click on the join button. Okay.
Amit, may I please request you to let me like move between the rooms? Amit, can you hear me?
Yeah, Sujata. Yeah. Okay. So, and maybe you can just ask the question or answer the Marcus, do you want to go anywhere? To any room in particular? Not responding. Chandra Prakash is not responding.
Hello. So for each element can be okay.
Was there any other question, Chandrima?
Hello.
I think Gauri was explaining the thing and the breakout room session broke down.
Okay, and here someone was saying, asking the tightness of question 10b.
Hello. Hello.
That's Dilworth's theorem.
Can you please pay attention here? Yeah, we are approaching the end of today's session. I have some important announcements to make. Can offline participants also pay attention here? Yeah, I have some important announcements before we wrap up this session. That tomorrow onwards, we'll have 1 hour and 15 minutes lunch break. We will update the timetable accordingly on the website. And most importantly, for those who are students amongst the participants, there will be an opportunity to do a presentation on the last day while working in small groups. And the announcements of the topics will be made tomorrow after the tutorial session on category theory is over. So at 5:15, yeah, same time. So please stay for that and make friends, work in small groups, and you have got 3 days, and last day is entirely reserved for student presentations. Okay, so our speakers have kindly sent us several topics for presentations where you can read something new and then present. Yeah, you will have enough time to do so. So we also need to end this meeting soon because the lecture hall will also be closed. This we have started this session on a gazetted holiday. Yeah.
Yeah. No, I would like to say that it's very nice. The student participation is really, really nice.
Yes,
So
it
they're
is.
actively participating in the tutorials, and I'm so happy about it. That's all I wanted to say.
Yeah, that's true. Sorry, I couldn't pay more attention to these tutorials. I had something to take care of.
Yeah. No, it's fine.
Yeah.
So just one comment I had. There was it's not to everybody. Somebody was asking about a question in the this thing in the about the tight bound of question 10. So that is exactly the Dilworth's theorem for those who know about it. And if you do not know, please have a look. Please Google. Search it. That's Dilworth's theorem.
Maybe you can type the name.
Yeah, I am exactly typing the name.
Yeah. Dilworth's theorem. Right. So any questions from the participants? In that case, let us close today's meeting. See you all tomorrow at 9:50. Hopefully you'll join 10 minutes before the session begins. 9:50, 50. Yeah. I'm asking them to join 10 minutes in advance. Yeah. Okay. Bye.